Welcome back. In this lesson, we'll see how to read digital inputs and debounce switches connected to them. Keep in mind that you can refer back to the PDF version of this tutorial, which you can download for free from the Gum Electronics website, to fill in any details this video skims over. For this lesson, we'll move to a slightly bigger baseline PIC, the 12F509. It still comes in an 8-pin DIP package, but it has 6 I/O pins instead of 4, so now all of the 8 pins are connected. The 12F509 has 4 times as much program memory as the 10F200, and more than twice as much RAM. Let's quickly modify our code from the last lesson to use the 12F509, firstly selecting the correct device in project settings. Having more memory makes no difference to the C code, but we now have 6 pins instead of 4, so I'll update the code to reflect that we now have 6 tris and GPIO bits. The 12F509 also has more oscillator options than the 10F200. We'll take a look at those in a later lesson, but it does mean that we need a different processor configuration. So I'll go to the configuration bits, as we did in the last lesson. This time, also select that I want to use the internal oscillator. Then generate the source code and copy it in. So why move to the 12F509 when we don't actually need any extra pins or memory for this lesson? It's just to show you that when you move to a different PIC in the same family, most of your code won't need to change, but some of the I/O initialization and configuration bits might, so it's worth checking. In the last lesson, we were still blinking LEDs. Now that's more useful than it sounds because, with appropriate drive circuitry, you can replace that LED with any on-off device you want to control. But unless your device will just run a fixed output sequence, it's going to need to respond to inputs from the outside world. And the simplest type of input, which we'll look at in this lesson, are digital inputs, on or off, high or low. We'll use a simple push button switch, but it could be anything that indicates an on-off status. We'll use a similar circuit to before, with an LED driven by GP1, but now with the PIC 12F509 instead of the 10F200, and a push button switch connected to GP3. The 1K resistor isn't really needed in this example, but series resistors like this help protect the PIC's inputs from high or negative voltages, or from short circuits if the pin is accidentally configured as an output. When the button is pressed, GP3 is pulled down to ground through the switch. Otherwise, it's pulled up to 5 volts through the 10K resistor, which is why resistors like this are called pull-up resistors. So, GP3 will be high when the switch is open, and low when the button is pressed. To build this circuit with the baseline PIC training board, make sure you remove the 10F200 from the 10F socket. Then insert the 12F509 provided with the board into the top part of the 12F16F socket. And close jumpers JP12, which connects the LED to GP1, and JP3, which brings the 10K pull-up resistor into the circuit. So now we've got a switch connected to a pin. How can we tell if it's open or closed? As we saw back in lesson 1, each GPIO pin can be configured as a digital input or output, except for GP3, which is input only. To configure a pin as an input, set the corresponding tris bit to 1. The state of each pin can then be read in the GPIO register. If the voltage on a pin is high, the corresponding bit reads as 1. If the input's low, it reads as 0. So if the push button is pressed, the GP3 bit will read as 0, otherwise it will read as 1. Let's start with a really simple example. We'll just light the LED whenever the button's pressed. Sure, you could do the same thing with a piece of wire, but hey, why not throw a microcontroller at the problem? As usual, I'll base this example on the initialization code and structure we've used before. Makes sense, right? But since we want to use GP3 as an input, we need to update the processor configuration to disable the external reset functionality that's otherwise assigned to GP3. And again, I'll clear tris bit 1 to make GP1 an output, and just state explicitly that bit 3 is set to configure GP3 as an input, even though GP3 is input only. We need to set the GP1 bit to turn on the LED whenever the push button is pressed, and clear GP1 whenever the button is released. We saw in the last lesson that the XC8 compiler makes it easy to access individual GPIO bits through structures defined in the header files. So for example, we can drive the GP1 pin high or low by writing 1 or 0 to GPIO bits.gp1. And to read the current state of the GP3 pin, we can simply access GPIO bits.gp3. Since we want GP1 to go high when GP3 is low, and vice versa, we only need to use the binary complement operator, like this. Okay, that's quite elegant, and it should work, most of the time. Remember the read, modify, write problem from lesson 1? Instead of modifying a single output pin directly like this, it's safer to write to the whole GPIO port in a single operation. So I'll use the conditional operator to write either a 0 or a bit pattern where GP1 is set to GPIO, depending on whether or not the button is pressed. Now if I compile this code and program it into the PIC, the LED lights whenever I press the push button. It's not very exciting though, is it? It'd be better to turn the LED on when I press the button and turn it off again when the button's pressed again. There's a problem with doing that though. Real mechanical switches have contacts that bounce. Too fast for human perception to be sure, but fast enough for the PIC to see the switch go on and off a few times, really quickly, whenever the button is pressed. Let's see that in action. I've hooked an oscilloscope up to a push button, so we can see what happens when the button's pressed. The output's normally high, and it'll be pulled down to ground when I press the button. The scope's been set up to trigger on that, so we can capture the button press. So I'll press the button, and bang, there it goes. But it's hardly a clean transition. I'll zoom in a bit for a better look. There are definitely a couple of good bounces in there. I'll turn on some cursors so I can measure them. We can see that in this case, for this switch, the bouncing finishes after 133 microseconds. The first bounce starts 72 microseconds in, and the shortest bounce is just 9 microseconds long, which seems pretty short, but it's still plenty long enough for the PIC to react to. So we need a way to avoid reacting to those short pulses. You can use hardware approaches to filter them out, and a simple hardware method is shown in the written tutorial. But you can also do it all in software, and that's what we'll look at here. Let's start with some code without any debouncing. First, wait for the button press. As long as the GP3 bit is set, the PIC sits in this busy wait loop. When the button's pressed, GP3 is 0, so I drop out of the while loop and move on to toggling the LED. I'll just go grab the code from the last lesson. It uses a shadow variable to toggle the LED. Then we need to wait for the button to be released, ready to be pressed again. Same as above, except that this time waiting for GPU1 to go high. You'll find that with this code, it's hard to make the LED change reliably, because each contact bounce looks like a new button press. So we need to debounce it. The easiest way to do that is to add a delay. The idea is simple. Respond to the button press immediately, so the device feels nice and responsive to the user, then wait a while, until we're sure that the button will have finished bouncing, before checking to see whether it's been released. Then we add another debounce delay, to be sure the button's stable after the release, before going back and waiting for the next button press. How long to delay? It depends on your switch and your application. The switch I tested before always finished bouncing within a couple of hundred microseconds, so a delay of a millisecond should be safe, but it doesn't hurt to make it longer, as long as the button still feels responsive to the user. 10 milliseconds seems reasonable, so I'll just add a 10 millisecond delay after toggling the LED, then again after the button's released. We're using XC8's delay macro again, so I need to define the processor clock frequency, the same as in the last lesson. We'll now find that you can reliably toggle the LED on each button press. There's still a potential problem though. Sometimes we get short spikes or glitches in input signals, maybe from some sort of electrical interference, but if you only have a simple debounce delay, there's no way to tell the difference between a glitch and the start of a switch closure. A common way to filter out spikes, as well as bounces, is to check that the switch stays consistently open or closed. When you detect that the button's pressed, you keep checking, until it's stayed down for long enough that you're confident that it's really pressed and it's stopped bouncing. You can do that by periodically sampling the input and counting the number of times it's still in the new state. In other words, if a switch reads on enough times in a row, it's really on. We can pretty much write this algorithm directly in C, using a while loop like this, where we're sampling the button every millisecond. However, it's possible to restructure the code as a for loop, like so. It's a little shorter, but more importantly, makes it a bit easier to see what's going on. Then we can debounce the button release in the same way, just with the opposite bit test. Finally, if you're not worried about responding to glitches from interference, there's actually no need to debounce the button press. If I delete the button press debounce, the press will still be acted on as soon as it's detected. And there's no need to explicitly wait for the button release, because the counting debounce algorithm is already doing that. So I can make the code a fair bit shorter, while still reliably toggling the LED each time a button's pressed. The code's fine, but there's still an improvement we can make to the circuit. This arrangement of using a resistor to pull up an input when a switch is open is so common that most microcontrollers, including PIC C, make them available internally. If you enable the internal pull-up, you don't need the external pull-up resistor, so it can go, and we're left with an even simpler circuit. To take the external pull-up resistor out of circuit on the training board, just remove jumper JP3. The internal pull-ups are controlled by the GPPU bit in the option register. The option register controls a few other things, which we'll take a look at in future lessons. But to enable the pull-ups, we only need to clear the GPPU bit. Like Tris, option is write only, and the XC8 compiler makes it possible to write to it through the option variable. The header files define symbols for the individual bits. The N in NGPPU stands for not. It's a reminder that this bit works in an inverted way, where we need to write a 0 instead of a 1 to enable pull-ups. So to enable pull-ups, you can use a statement like this, where the NGPPU bit is inverted. And while I'm updating the initialization code, I'll add something I should have included before. Initialize GPIO, so that the output pin states are defined when the code starts. When you compile this, you'll find it now works fine, with no external pull-up resistor. And that's as far as we're going to go for baseline PIC video tutorials. We've covered most of the baseline PIC core and general purpose I/O. So from this point, it's mostly about learning how to use the PIC's peripherals, such as timers and analog to digital converters. There's certainly something to be said for learning the baseline PIC peripherals, because they're relatively simple and easy to learn, but the reality is that baseline PICs are unlikely to be a good choice for new designs. For example, they're not supported by Microchip's new low-cost Snap programmer. So I'll be covering the PIC peripherals in the enhanced mid-range PIC series. See you there.